Hello, summer AP physics students. I hope my audio is coming out because I've been having some problems with my computer audio, and you might have to bear with me until I go down and get a microphone. I left my microphone at school. Maybe I'll just drive up tomorrow and get it if I can. Anyway, welcome. I just want to begin by talking about why physics is so exciting. And it's exciting because it is the study of the fundamental laws of nature. Chemistry, I love chemistry, but chemistry, if this were talking about our sort of description of nature, would be about that big, and you know, we talking about everything from, let's say, the neutrons and protons and electrons up through and including uh, major chemical reactions and descriptions of chemical systems, including kinetics, equilibrium, thermodynamics, all that sort of stuff, electrochemistry. But that's only one little fraction of the spectrum of the description of the universe. Biology, we're going to talk about biology. Well, biology might talk about, maybe that much of the description of our universe. But physics keeps on going. Physics encompasses chemistry. It encompasses biology. It encompasses uh, every aspect of what I consider to be important scientific discussions about our world. So um, I can sort of consider everything a subset of physics. Physics is different than pure mathematics. Pure mathematics is very exciting, but in many cases it doesn't do a lot to describe our universe. Well, I guess that's not really true because there are branches of mathematics that indeed do describe uh, the world around us. But let's just consider physics to be super exciting, and I'm super excited to teach it. We use formulas in physics, and we need to be very, very competent, very nimble in being able to manipulate formulas and to solve for certain terms in an equation that we need. We're going to talk about that. But the formulas describe the beauty of the universe. I could write a formula that you should all know. PV equals nRT, right? We see that in chemistry, but that's a physics idea. I mean, talking about the relationships between pressure and volume, and amount, and temperature, those quantities are related through this formula. And by now, hopefully, all of you should be very comfortable if I said, "Hey, solve this for number of moles n." Well, that'd be PV over RT. And I want you to get to a point where you look at a formula and you don't even really have to think about it. You can just describe that relationship in your mind and manipulate it in your mind. And that, to me, would be the place we want to get to. What I do want to talk about, though, now is this idea of MKS units. MKS units, and that stands for meter, kilogram, and second. And uh, if you remember in chemistry, I used brackets like this, and that meant concentration. But in physics, that means dimensionality. So if I have the unit for length, or the concept of length, rather, in these brackets, the dimensionality that we will choose to use will be meters. And then if I'm looking at mass, the dimensionality that we will be using most of the time will be the kilogram. And the dimensionality for time will be the seconds. So in that respect, we have the meter, kilogram, and second. Now that's not to say that we will not be discussing other units. We might want to use feet or yards. I don't know why. And for kilograms, maybe we'll be talking about grams at different times. And seconds, we might be talking about milliseconds or hours or something like that. But the important thing is when we start doing uh, the, the the equations, the work in physics, we need to be able to convert back to these units because these are the units upon which many of our other units are built. Um, um, let's just talk about some of these different things here, and you can get a feel for something. You know that a meter is pretty much about the same as a yard. It's a little bit longer than a yard. Um, there are 2.54 centimeters in an inch, and that's a conversion factor. And so you can go ahead and figure out in 36 inches how many centimeters there are. And maybe I'll let you do that as an exercise. Um, Kilogram, if you had to sort of wrap your mind around that, that'd be a little over 2 pounds. Now, again, I'm mixing up mass, kilograms, and weight, pounds, but just so you have some sort of a point of reference. About 2.2 pounds in a kilogram. And you know what a second is. Um, but we might be talking about milliseconds, we might be talking about hours, days, uh, but you'll have to go back and convert much of the time to do problems in physics. So let's just take a rough idea about some of these ideas of meter, kilogram, and second. Take a look at kilogram. An average human is around 70 kilograms for a human. So, 2.2 pounds per kilogram. So you're talking about something, it's about 184 pounds or something like that, if you do the math. And so we can envision that. We can envision that an elephant is pretty big, it's about 5,400 kilograms. A baseball is about 0.15 kilograms. And an electron, very tiny, 9.11 times 10 to the minus 31 kilograms. I mean, we could wrap our minds around 70 kilograms. We can even wrap our minds around an elephant at about 5,000 and change kilograms. Baseball, we know what that is, but 10 to the negative 31 kilograms, tremendously small. And that's what's so beautiful about physics. It really spans, wow, 45 orders of magnitude. Orders of magnitudes are multiples of 10. So we're talking about subatomic particles that make up the things like the proton. The proton is made up of quarks. Quarks are subatomic particles that go into making up these atomic particles, or this is a subatomic particle as well, but quarks go out into making up these particles. So for example, a proton would be made up of 3 quarks, and those quarks would be, they have a spin to them. They'd be up, up, down. That would be the 3 particles that would make a proton. A neutron, on the other hand, neutron would be up, down, down spin for the quarks. By the way, these two have approximately the same mass of about 1.67 times 10 to the negative 27 kilograms. Very tiny indeed. And quarks, we won't be talking much about subatomic particle physics in this class, but we might mention it toward the end of the year because it's kind of interesting. So you get the idea that we have very small things, and like I said, 45 orders of magnitude. We go from the smallest things like the quarks and the electrons. Electrons are extraordinarily tiny as well. Electrons are a fundamental particle. They are not made up of any other particles, by the way. So going from something like this all the way up to the expanse of the galaxy, which is, like I said, about 40 or 45 orders of magnitude greater than this end of the ballpark. So there's a great video called Powers of 10. If you've not watched it, I suggest watching it. I can always post a link to it, and it might be something that you would be interested in seeing. I think I showed it at the beginning of chemistry class. So again, mass goes from very small to very large. Length, we know that a football field is about 100 meters, okay? And we know that the distance from the Earth to the Sun, well, if you were going to figure it out, it's 93 million miles. So if you wanted to figure that out, that's about 1.5 times 10 to the 11 meters. So that's a big distance. But on the other side of the coin, the diameter of a hydrogen atom is very small. So you've got a hydrogen atom. If I look at the diameter of a hydrogen atom, we're talking about 10 to the minus 10 meters. Pretty tiny stuff. So Anyway, this is just a little bit of a, you know, Monday afternoon rambling about some stuff that I find interesting. Now, I want to go back to this idea of dimensionality of things. We haven't talked about time yet. Time was in seconds. And again, let's remind ourselves of these things. Length, we're going to be focusing on meter, and mass, we're going to be focusing on the kilogram. So let's go ahead and see what we can do with some of these things. Um, anyone have an idea what the average human lifespan is in time, by the way, in seconds? Maybe you can go ahead and figure that out. And it's somewhere around 2 times 10 to the 9 seconds. So I'm I'm a little bit over halfway there. So you guys have many more seconds left than I do. So one of the things I'd like you to do, though, is also understand the metric prefixes. So if you're talking about, for example, a meter, that's equal to 100 centimeters. And if I'm talking about something like a kilogram, well, 1 kilogram is equal to 1,000 grams. I don't have to rehash this stuff. You're seniors now, and you should really know how to convert back and forth between these things. So if you still need to go ahead and look at that, go ahead to the um, table 1-4. I think I also put a video up. If I haven't put one up, I can certainly do that. But you're hopefully pretty comfortable with this stuff by now. But let's take a look at some dimensions of units. Now, the dimensions of units, our life would be pretty boring if we were just left with second, meter, and kilogram. We couldn't do too much physics with just those three units. But if we combine them, we can do a whole bunch of stuff. We know that distance, oftentimes represented by x, in our case, in physics, in one-dimensional motion, or x and y in two-dimensional motion, and x and y and z in three-dimensional space. Well, let's take a look. If I'm just talking about length, well, that's just meter, for example. But if I'm talking about area, say I have a square and I want to be interested in the area, that's going to be length squared. So in our case, that would be square meters for area. If I'm talking about volume, all of a sudden I have a cube. See if I can make this into a cube. Well, then we're going to be talking about length cubed. So in that case, we would call that cubic meters. You could actually put the exponent inside of the bracket. That's all this is saying. Well, what is the dimensionality? Well, so those are pretty easy. Area and volume. But if we start combining things, we say, well, what happens if I'm traveling along, I'm going a certain distance x in a certain amount of time, t? Well, if I'm going a certain distance x in a certain amount of time, well, we could talk about length divided by time. And in this case, our unit would be meters per second. And that would be our unit for speed, or more importantly, velocity, which is different than speed. We'll talk about why that is, but just for the sake of our discussion today, understand that velocity and speed will have this unit meters per second. The difference between velocity and speed, well, let me hold on because I need to talk about displacement. I'm not going to talk about that today. If I'm changing speed, let's say, for example, I'm plotting my speed, my speed, I'll call it speed for right now, versus time. And, if I'm just traveling like this, my speed is staying constant for a given time. I'm going at a constant speed. But if my speed starts increasing with time, it's changing. I'm getting faster with time than I am accelerating. So if I'm accelerating, my speed is distance per unit time, meters per second, per second. So I'm going to have to put a squared on that there. And indeed, my unit is meter per second squared for acceleration. It's meters per second per second. um, we can, and this would be acceleration. You may think I'm wasting a lot of paper here, but that's okay. Let's take a look at our first physics equation, and let's see if dimensionally we can show that it's correct. This is a very famous equation. We're going to be learning it in an area called kinematics, which is kind of where we run out of the gate, so to speak. In physics, it says that my position at any given time is related to my initial position plus the velocity with which I am traveling initially times time that I'm traveling plus 1/2 AT squared, where A is acceleration and T is time squared. We're going to get very familiar with this equation as we move through the first chapter or so, or second chapter in the book. Well, let's just look at this thing dimensionally without worrying about what these terms mean too much. We kind of have an idea because I went over that a little bit. Well, on this side, I just have length. Okay, so all of this stuff, when I go ahead and do dimensional analysis on this, all of this stuff better give me length. Okay, so let's see here. I've got my x sub 0, my starting point. Well, that's going to be a length. And then if I go over here, I've got v0 times t. Well, let's go ahead and figure out what velocity was. That was length per unit time. And now time, of course, has units of seconds. So dimensionally, those are going to cancel. Plus 1/2. Now let's look at acceleration. We learned that acceleration was length per time squared. And I'm going to multiply that by, well, seconds squared, time squared. So, well, I guess it doesn't really matter where I put the exponent. You get the point. I've got length plus length plus length gives me length, which is exactly what I need to do. You have to understand that things are dimensionally correct. So what I'd like you to do, I put up a sheet online, a PDF, and what that PDF has you do, it has you rearrange equations. And if you rearrange equations, hopefully you'll have no trouble with that. Work through the odd problems, I guess. And if you feel like you need more practice, work through the even ones. And send me a picture of your work. So, in other words, you might see an equation that looks something like this: K equals 1/2 mv squared. This is an equation for kinetic energy, and it might say solve this equation for velocity. So what you're going to do, if you want to solve this equation for velocity, you're going to want to isolate the variable, make a brand new sentence. V equals 2k, oh, I'm writing an E here for energy, 2k over m, and I have to take the square root of it. So, and oftentimes, obviously you put a plus or a minus, but we're very often going to ignore the negative sign there. So we oftentimes just look at the positive side. Not all the time, but most of the time. You could also write kinetic energy this way. I just Ke for kinetic energy. That's one term. Don't get it confused with two different terms. One of the things that's going to frustrate you about physics is you're going to be seeing different notation for different things. Sometimes kinetic energy is given the symbol capital T, and potential energy might be called U. And you might see an equation that looks like that. I don't want to go into this too much now. It's an equations of motions for Lagrangian mathematics. This is something you study in college, not so much in high school, that's for sure. But I just want to show you there are different ways to represent different things, different ways to represent the same things. For example, you might see velocity written as v in class. And you'll have a v, maybe if you're starting out, you'll have v sub 0. That's initial velocity. You might see v sub I, initial velocity. You might see v sub t, the velocity at some time t. You might see v sub f, final velocity. You might see it written in some book. Uh, this v velocity might be written as x with a little dot above it. So you're going to have to get used to different symbols for the same thing. And I know that's a little bit frustrating. Anyway, I've talked for 20 minutes already, and I could talk for 200 more, but I'll be doing that a little bit later. So let's get started on the stuff. Take your time, enjoy your summer, but get the stuff done. And if you're running a little late on something, don't worry about it. My deadlines kind of have, built-in buffers for you to say, hey, I'm going to go on vacation this week. Can I get it to you next week? That's fine. You guys know me by now. All right, well, enjoy, and hopefully my audio is working. I'll check it out. Take care, guys.